Introduction.
I like to drink the juice as it is nutritious. Juice tastes good, especially when it is chilled. Yeah, I agree with you. Please pass the ice cubes to me. I want to put 1 or 2 more into my glass. Sure. Ashish, I want to ask you something. Yeah, sure. Why ice cubes are melting down? When we put the ice cube into the juice, then also it gets dissolved. Why? Okay, I'll tell you. Melting of ice is an example of thermodynamics. Nothing in the universe is cold, you see. Everything in the universe radiates heat to its surrounding. The entropy of universe is continuously increasing. Due to this entropy, ice cubes are melting down. Okay, now I got the answer of my question. It is quite interesting to know about that fact. I want to know more about that. Can you please tell me? Objectives. At the end of this lesson, you'll be able to define thermodynamics, explain thermodynamic process, understand mode of transference of energy, describe internal energy, understand pressure-volume work, define enthalpy, differentiate extensive and intensive properties, know about calorimetry, analyze relationship between delta H and delta E, explain laws of thermochemistry, understand bond enthalpies, define spontaneous process, thermodynamics. The branch of science which deals with the quantitative relationship between heat and other forms of energies is known as thermodynamics. Thermodynamics is primarily based upon 3 fundamental generalizations. First law deals with the equivalence of different forms of energies. Second law deals with the direction of chemical change. Third law helps to evaluate the thermodynamics parameters like entropy. Basic terminologies in thermodynamics. System. A system is defined as that part of the universe which is under investigation. For example, if we are studying the effect of temperature on the properties of water, then water will be taken as the system. Surrounding. The part of the universe other than the system is known as surroundings.
For example, if a reaction mixture is taken in a test tube, the reaction mixture constitutes the system. The walls of the test tube constitute the boundary, and everything else is the surroundings.
System may be classified into 3 types. Open system, closed system, isolated system. Open system. A system which can exchange mass as well as energy with the surroundings is called an open system. Closed system. A system which can exchange energy with the surroundings but not mass is called a closed system. Isolated system. A system which can neither exchange mass nor energy with the surroundings is called an isolated system. State of the system. State of the system refers to the conditions of existence of a system when its macroscopic properties have definite values. For example, the state of gaseous system can be defined by its pressure, volume, temperature, and amount. Once these minimum numbers of macroscopic properties are fixed, the other properties automatically acquire definite values. Variation in one or more macroscopic properties brings a change in the state of the system when other macroscopic properties attain new values. The macroscopic properties are thus called state variables. Initial state refers to the starting state of system in equilibrium. After interaction with surroundings, the system attains another equilibrium state, which is referred to as a final state of the system. Thermodynamic process. The operation which brings about the changes in the state of the system is termed as thermodynamic process. A thermodynamic process may be further classified into following categories. Isothermal process. It is a process which is carried out at constant temperature. Adiabatic process. It is a process in which no heat exchange occurs between the system and the surroundings. Isobaric process. It is a process which is carried out at constant pressure. Isochoric process. It is a process which is carried out at constant volume. Mode of transference of energy. The exchange of energy between the system and surroundings can occur in two important modes. Heat. The transference of energy takes place as heat if the system and surroundings are at different temperatures. If the system is at higher temperature, the energy is lost to the surrounding as heat. If the system is at lower temperature than the surroundings, the energy is gained by the system from the surroundings. Heat is represented by Q. Work. The transference of energy may take place in the form of work if the system and surroundings have different pressures. Let us consider a gaseous system which is enclosed in a cylinder fitted with a movable piston. If pressure of the system is higher, the piston will be pushed up until the pressure of the system becomes equal to the pressure of the surroundings. If the system is at lower pressure, piston will be pushed down until the pressure of the system. Internal energy. Internal energy is made up of kinetic and potential energies of the constituent particles. The internal energy is a state function, and the internal energy changes when heat is transferred from system to surroundings or from surroundings to system. The internal energy of an isolated system is constant. The internal energy of a system can be changed into two ways: by allowing heat to flow into the system or out of the system, by work done on the system or by the system. The change in the internal energy is given by delta U equals Q plus W, where Q is the heat supplied to the system, W is the work done on the system. The above relation is the first law of thermodynamics. Pressure-volume work. Consider a cylinder containing a gas is fitted with frictionless piston. If the external pressure is slightly lower than the internal pressure, then the piston will move upwards to a length until external pressure becomes equal to the internal pressure. If the volume and cross-section of the cylinder is V and A respectively, then work done by the system is equal to P into A into L, which is equal to P into delta V. Reversible PV work of an ideal gas. Consider an ideal gas be enclosed in a cylinder of volume V, fitted with a frictionless piston, and the external pressure is P. If the difference of pressure is infinitesimally small, then increase in volume is also infinitesimally small. Now, work done by the system due to pressure-volume work is also small. The total amount of work for expansion of an ideal gas from V2 to V1 against a constant external pressure P is given by minus 2.0